Okay, I do not see Michael, nor Reagan, nor Jaron, nor Sade. Is that correct? All right, let's get started. We're going to talk some more about moving charge. We actually won't finish chapter 22 today, so do the for the concept coach, do the first piece in chapter 23 for Monday. If you've already done that first piece, then just don't worry about it. The concept coach grades. I've been thinking about how to give people grades that are going to fairly represent effort as well as answers, right? Because I don't want people to be like, I go through and I do these each time and I get 60% and I feel like I'm going to fail this area. So what I am going to be doing, I have been faithfully recording progress at 10:25 each lecture day, and then I will record your scores after the exams. So I was going to do it yesterday during the exam, but then I went to the honors meeting instead, the Union Scholars. So hopefully this afternoon get them recorded. But I will record your grade, and at least right now I believe this is the formula I'm going to use. That I'll take the score that you had on exam date and divide that by 2. And let's see, did Ray? No. Who else came in? I had Jaron that came in and Michael. And then I will add 50% if you had completed it on the due date. So, like if you got 60%, you would have 30 plus 50 is 80. Right? So, raising the grades to try to help out people who are missing things. And also, notice it's the score on the exam date that I'm recording there. So if you didn't get it done on time, you still can get some points, because the whole reason for this concept coach is for your learning, not for the grade, right? The grade is just a way to encourage people to go through the learning process. And so that's my plan with the grades right now. It could change a little bit as I realize, I made a mistake somewhere in how I'm figuring this, but I'm trying to give people incentives to learn from the concept coach and, scores commensurate with effort. Yeah?
Wait, you're saying, so this is for concept coach or is this for exam?
For concept coach.
So if we get 100% concept coach, but we fail our test, then you're just going to get a grade?
This is only concept coach. This has nothing to do with the exam. The only reason it has for exam is this is the concept coach score on the date of the exam.
I thought you were saying our exam score.
Right, so like if you fell behind, because doing those concept coach things should help you for the test, I'm giving you some points for doing it after it was due, because it's beneficial to you to do it. But this is all concept coach. None of this has exam scores in it. And what was it I said? 10 sections you can drop, which is about a chapter on average, or 2 to 3 lectures worth. That's what I calculated for. Any questions on this? I want to be, of course, as transparent as possible. I don't want my grade scheme to be some state secret. All right. First question of the day. Which statements are true about electric and magnetic forces on an electric charge? This is a multiple correct answer, so put in all the ones you believe are correct and hit enter. Like Lindsay did. Okay, we had a big change there at the end. For a long time, it was basically going from low numbers to high numbers, top to bottom. Now it's better, because the two that garnered a majority of the students are indeed the two correct answers. Both forces are proportional to charge, and both are proportional to field strength. Now the equations are very different. Which one is simpler of the two? The electric. The electric force is equal to charge multiplied by electric field. Only those two things. Really simple. It's proportional to the field strength. The magnetic force is equal to QV cross B. Just to make sure I haven't lost anyone, what does Q stand for? Charge. What does V stand for? The velocity of the charge. And what does B stand for? Magnetic field. And what does the cross product mean? You multiply the perpendicular parts and you get a direction that is perpendicular to both of the two initial pieces. We use the right-hand rule to get that direction. The right-hand rule is going to be something on the next test you're going to have to know. It gets a little funny when people are taking the test and you see people, trying to get the right hand right. Always remember that you can rotate your paper when you're trying to apply the right-hand rule so that you can make it so you don't have to get your hand in some crazy position. So, this one here, well, let's start with the blue one. The blue one, the force is perpendicular to the field, the magnetic force. But the electric force was parallel to the field. So one's parallel, one's perpendicular. That's why neither of those was a correct answer. And only the magnetic force depends on speed. The electric one doesn't. So that's why that was an incorrect answer. So what if I have a charged particle moving in a region with both an electric and a magnetic force? Well, then the net force will be the sum of the two. So force electric field plus force magnetic field. And what about the special case where the net force is zero? If the net force is zero, what does that tell you about the motion? It's constant motion. There's no acceleration, which means no change in direction, no change in speed. So you can have a charged particle moving through electric and magnetic fields where there is no net force. And for that situation, you're going to have the electric force plus the magnetic force equals zero. By the way, let's notice the directions. Well, I'll come back to the picture. At the end of the next slide, then I'll come back to this one. So if we add those up and they're equal to zero, notice I had charge in both because they were both proportional to charge. So I can divide out the charge. So I divide out the charge and then solve for electric field. And electric field is minus the velocity cross magnetic field. When is that true? Only if the net force is zero. Don't try to say this is always true. But if the net force is zero, the electric field has to be equal to the velocity minus the velocity cross the magnetic field. What is a simpler way I could write minus velocity cross magnetic field? No? Simple rule of cross products. What happens if you reverse the order? If I reverse the order, what changed? Right, the sign changes. So this way here, it doesn't have the minus sign. Going once again to a condition, there is a net force on the particle of zero only if it turns out that the speed is the ratio of the electric field divided by the magnetic field. That comes from the relationship up above. And the direction of the velocity has to be in the direction that is correct. How do we determine the correct direction? By looking at that cross product. If I take E is equal to V cross B, well, minus V cross B, let's just take this one here. E is equal to B cross B. What direction should I have my index finger? Direction of the magnetic field. What direction should my middle finger go? The velocity. Everyone else that's not Tori, how did she know those? For the right-hand rule, your index finger is always in the direction of the first thing in the cross product. And so since I asked B, which is the first thing, or I asked index finger, she looked in, B was the first thing, so she said B. Middle finger in the direction of the second one was V. And then what gives me the direction of my answer? My thumb. Now, going back to the preceding picture, the slide, had this set up. And so we can look at this and verify if I take the direction of V is in the direction of, what did I have? Okay, now I don't remember what I had written there. And I don't have it on this, so I can't look. I have to come back. Okay, E is in the direction of V cross B, or that minus B cross B, or nice writing. So B cross V. So let's just look at B cross V now. So if I take B in this picture, that is going up, and then V is coming out here. My thumb points that way, in the direction of E. So we can see the relationship for the directions. All right, so that was motion with a constant motion and electric fields and magnetic fields. Now, how do we use this? How do we make this useful to science? One way is by using a velocity selector. So in this picture we have an ion source. What's the ion source? It could be lots of different things. You know, it could be like, in my research, I had a piece of magnesium oxide and I hit it with an ultraviolet laser. And it vaporizes the material and I have ions that come off. And then those ions go through, well, there's first a stage to speed them up. How would I speed up the ions? Okay, the magnetic field doesn't speed them up. Remember, we called that a turning force, steering force. So you use an electric field. So if, for instance, you have a positive ion, you have something that electrons been kicked off of, if you have it go from a higher voltage to a lower voltage, it's going to have a drop in potential energy corresponding to an increase in kinetic energy. So you speed it up by putting a voltage difference to give it a good speed. But then you want to select just one speed. And so to select just one speed, you put electric and magnetic fields crossed here. So the electric fields, I believe, are the green ones. So if the green ones are the electric field, what direction would the electric field make a positive particle move? What direction is the force caused by electric field?
Oh, electric field. Oh, sorry.
Parallel. So because the force is parallel to the electric field, a positive charge would be deflected in this direction from the electric field. Now the magnetic field is going down into the page. So my force would be force is equal to QV cross B. Take my right hand, put my index fingers so they're pointing the direction of V, which is going that way. And then orient my hand so my middle fingers can point into the screen because we have the X's for the magnetic field, and my thumb points up. So the magnetic field is going to make the positive ions, do this. I should have done it that way. And if we have just the right speed, and what was that right speed?
It's equal to E over B.
If we have the speed as E over B, then the net force will be 0 and it will go straight through. If it's going slower, which force got smaller? Which one? The magnetic. So if it goes slower, the magnetic force gets smaller, and it's going to do what the electric force was making it do, come down this way. If it's going too fast, the magnetic field is stronger and it'll swerve up. And so only ones with just the speed we're looking for will make it through. So that allows us to have a known speed for our particles, and then we have over here just a magnetic field to make them curve for separating them by mass to charge ratio. So this is more specific on how we make a mass analyzer. Here's another, here's a description talking about going through the voltage difference, so you have the change in potential energy. And this is showing a cathode ray tube. The cathode ray tube, we'll come back and talk about it later, but this was a significant advance to man's understanding of nature. Previous to this, there was some knowledge about electrons, but not that electrons were part of all of our matter. And so this experiment, you had the cathode there that kicked out particles that in a mostly evacuated tube would make a glow. And they found that a magnetic field would make it change its path. And an electric field would make it change its path. So if a magnetic field or an electric field will make it change its path, then it must be a charged particle. And so then they did experiments with the crossed electric and magnetic fields so they could learn more about the particle, about its charge. And eventually they determined that these cathode rays were electrons, so that matter had electrons in it. And so the nature of matter was revised to a model that had a bunch of generally positive slurry of paste with little, like raisins, of negative charge for the electrons. And of course, we'll learn a lot past that as well. But this experiment done by Thomson is a very important experiment for our understanding of nature and involved this aspect. Another one. Let's say you want to find out how fast the blood is flowing in your veins. You can do that. First, you have to cut down to get the vein. None of us like to be cut down, right? And then you can measure the voltage difference on the vein when you put it in a magnetic field. Because when you put that vein in a magnetic field, if you have ionized things moving in the blood, those ionized things are going to have a magnetic force, so that you'll have positive charge deviate one direction, negative charge deviate the other direction, and you'll create a charge separation. That charge separation, of course, creates an electric field, and so the amount of charge separation you get is going to be just enough to make it so you reach an equilibrium where charged particles now just go through without being deviated. And so you're going to have the same relationship we've just been looking at between the electric field, the magnetic field, and the voltage. So, put it in a magnetic field and measure the voltage difference on the vein, and you can determine how fast your ionized material is going through the vein. Kind of cool, right? And I'm sure there's a medical reason for it. The Hall effect, I think it's the back project, isn't it? Or is it I think it's the back one, was a project that was done last year for measuring the magnetic field. The Hall effect is basically what we saw with that measuring the rate of blood flowing in a vessel or artery. You have charged material that's moving in a magnetic field that's going to create an electric field. And you measure the voltage to determine what that electric field is, so it's called the Hall voltage. The electric field itself is called the Hall field. So here's a picture. Nope, not yet. Here's a picture and description of how the Hall effect works. You have this little wafer. I think they're pretty much semiconductors. And in that wafer, you put a magnetic field, or you take this probe and you put it in an unknown magnetic field. And knowing the drift velocity, you put a current through there, and the drift velocity is something you have to know. We'll learn later a different way of doing it, later being later today. You can calculate what the drift velocity is, and then you have your relationship between the velocity, the electric field, and the magnetic field. You measure the voltage difference, and remembering that if it's uniform, the voltage difference is equal to the electric field times the separation, which in this case was called W. So you have the electric field can be determined from that voltmeter, and since you have the relationship that VD is equal to E over B, then I can just say that's equal to the voltage difference over the width times the magnetic field. And then I can solve that for the magnetic field as a function of the voltage difference that's generated, the width of that Hall effect probe, and the voltage and the drift velocity. And so that's how a Hall effect probe works. Just measure that voltage, and then using those relationships, you get what the magnetic field is.
So what is the Hall effect?
The Hall effect is the effect that when you have charged particles moving in a magnetic field, they're going to deviate and create an electric field.
Oh.
Okay, now we're going to shift to talking about current carrying wires. That's the other way we can look at the Hall effect probe, is by just using the current carrying wire. If I have a current carrying wire, there should be moving charge. And we learned that a moving charge in the presence of a magnetic field will experience a force. So a current in the presence of a magnetic field should experience a force. The question is, what's the equation that relates the current in the magnetic field to the force? So we start here with the equation for the force of a single moving charge. If I have a current, that means I have something like a wire with a lot of single charges moving. And so we just say, okay, one charge moving, it would be the average force, force per charge, is the charge of that one charge. If it's a wire, that's going to be charged with an electron, multiplied by the drift velocity for the electron crossed the magnetic field. So if I have a whole bunch of electrons moving, the total force is just going to be the average force times the number of electrons moving. So the second line, all that's been done is we said, instead of the average, we take the total force is equal to N times the average force. So that's all that's been done between the first and second lines. But then we recognize that current is the charge density multiplied by the charge carrier, multiplied by the area, multiplied by the drift velocity. And so I can take the number of, capital N here is the number per unit volume, times volume, in other words, the number. And it's going to be equal to this density times length times area. This is repeated here, and then substituting N is equal to NLA, we get this relationship here. And now, for the grand victory, I usually don't even go through this, I just jump straight to it. This stuff here that we had with VD is current. So all of this stuff that we had, QV, turns out to be the same as current times length. And now there is a technicality that frankly I don't really care about, but I just want to explain to you so you have the technicality there. Technically, current doesn't have a direction. Current density has direction, not current. And so we define a different vector, the length vector, that is the length of the wire in the direction the current is flowing. Current's not a vector, but the length vector is in the direction the current is flowing. Right? It seems kind of silly. It's a technicality. I am just as comfortable writing Li vector except for I is not truly a vector. But it just feels right to me because in our circuit problems we drew an arrow for the current, right? If we can draw an arrow for its direction, it seems I should be able to call it a vector. Technically I can't. So putting this together, the magnetic force can be calculated either talking about the current flowing through a wire or a single charge traveling with speed v. Either one gives you the equation for force. IL cross B. How do you find the direction if it's IL cross B?
Presumably point your index finger in the direction that L is, and your fingers in the direction of B.
Right. You use the right-hand rule again. Anytime you have cross product, you just use that right-hand rule. So, yes, here's the finishing out equation. I just talked about it. We shall move on. How do we solve problems with wires with current flowing through them in a magnetic field? So here's some steps. The magnetic force is 0 if, and we have the three cases again, same three cases essentially that we had before. If the current is 0, if the wire is parallel to the magnetic field, or if the magnetic field is 0. Right? Before we had if the charge was 0, if the velocity is, no velocity, yes, if the velocity was parallel to the magnetic field, or if the magnetic field was 0, or if the charge, speed, or magnetic field were 0. There's actually one more that I didn't say. Then determine the angle between the length of the magnetic field, just like we did before, between velocity and magnetic field. And then the magnitude is ILB sine theta, where theta is the angle between the two. And you find the direction using the right-hand rule. All of that is just like we did before. Hardly worth repeating, except for it reminds you. So, a little example. A 125-meter long power line is horizontal, as shown here, and carries a current of 2,500 amps toward the south. It's a pretty big current. The Earth's magnetic field at this location is 0.052 millitesla toward the north and inclined 62 degrees downward. So this side here is north, this side here is south. Of course, that's downward. It says down here north and south, I guess. What is the magnetic force on the power line? We're going to have two things to worry about, the magnitude and the direction. So first, let's do the steps that we're given. Is this going to be a situation where the force is 0? No. You always ask that question first because then you can ignore the rest of them. So then the second question is, what is the angle between the magnetic field and the current? It's real trivial. I'm not asking a tough one. It's 62 degrees. Now, somebody might have said, no, I think you should have said 118 degrees. Sine of 118 is equal to sine of 62. It doesn't matter which one I used. Right, 118 would have been this angle here. But sine is symmetric around about 90 degrees, so it's fine either way. So the angle is 62 degrees. So I have my first step. What's the next step? Yeah, the magnitude. So the force is ILB sine of theta. So the current was 2,500 amps. The length was a really long length, 125 meters. The magnetic field was 0.052 milliteslas, and then sine of 62 degrees. I'll let one of my fine students calculate that for me. Yes, you'll want to take that milli out.
So I typed in the numbers correctly. I got 14.3.
14?
Yeah, I might have typed in the wrong one. I got 1.84. I probably typed it wrong. I got 14. Not those ones.
Okay, we had two people that said 14, so I'm going to go with that one. 14 point what? So we have 14.3 newtons. If it's wrong, it's wrong. It's calculator error, and that does happen. Next step is the direction. How do I find the direction of this force? Right-hand rule. So let me have Austin take us through using the right-hand rule on this to find the direction of the force.
Point your first index finger on the first units equation, so the I, so this way.
Right?
And then it'd be going the same way, right? For the
You keep your index finger pointing that direction, and then you rotate your hand so
that's
your middle fingers are pointing the direction of B.
so it's on the direction B, so it's coming out.
So it's coming out toward you. Now, if that's north and that's south, then it must be east. And so we have the force is this big and pointing east. Easy enough? Another clicker question. What direction is the net force on this loop? So this is a loop with current. The brown arrows are showing the current going around the loop. The blue arrows show the forces. Still waiting on 2. I know the last person is working on it, so that's why I'm waiting. Okay, everybody's answered. We have a smorgasbord of answers here. But we do have a very slim majority that says the net force is 0, so no direction. Now, when you look at this, first of all, how do you find the net force? You add the forces as vectors. We have one force that's up, one force that's down. There's only a force 4 and a force 2. What about force 1 and force 3? Why is there no force 1 or force 3 shown? Because the current is traveling parallel to the magnetic field. So there's no force. That's one of our 0 situations we don't have to think about. So we only have 2 forces acting on the wires due to magnetic force. We obviously are going to have some other forces maybe to hold it in place. And so then we take those 2 forces. Each force is going to have the equation for its magnitude. Force is equal to length A times current I times magnetic field B times sine of, what's the angle between the current and the magnetic field? 9 degrees. So they're the same force for both of them because they're both length A wires, the same current I going through, so they're equal magnitude, opposite direction, they add up to 0. So, if I let this thing run, what's it going to do? That is, if I just let it sit there, what's it going to do? It's going to spin. It's not going to move up or down. It's not going to accelerate up or down because the net force is 0. But net force equaling 0 is not the only equilibrium necessity. The other equilibrium necessity is the net torque is 0, but this does not have a 0 net torque. So let's calculate, it's coming up in the next slides, but let's do it here. Let us calculate the torque about this center axis. So first, what's the equation for torque? Torque is equal to okay, except for it has to be distance crossed to force. Torque is R cross F, and that order is important because it reverses the direction. So the R is the vector that points from the axis we're calculating torque about to where the force acts. So for side 2, what direction is R? Okay. For side 2, R is, and I will just draw it with a nice red arrow. There's R. So what is the length of R? 1/2 B. For people who didn't see it, B is the dimension in this direction, and A is the dimension in this direction. They're shown inside the picture. In fact, I've written my arrow on top of the A that's inside the picture. So now if I take torque for force 2, that's R2 cross F2. To get the magnitude, what's the angle between R and F in this picture? 90 degrees. In this picture, it's 90 degrees. It won't always be 90 degrees. So I have my R, 1/2 B, times my force, A, capital I, capital B, sine of 90 degrees, times sine of whatever this angle is, which right now is 90 degrees. I'm going to leave it with the sine theta because we'll come back to it later. What about its direction? Right hand rule. Take my right hand, put my index finger parallel to R, or so my middle finger points the direction of the force, and my thumb, okay, R is this way, my thumb is actually pointing up toward that direction. So I have a torque. Let us define that direction as Y. So that would be in the Y direction. Now that's the torque on one side. What about the torque on the other side? What's the radius on the other side? It's going the opposite direction, and the force is also going the opposite direction. They're the same magnitudes for the radius and for the force, but the directions are opposite. So if I do the opposite directions, take my right hand and put my index finger that way, orient my hand so my middle finger can point out, my thumb is again pointing in the Y direction. And so torque 4 turns out to be exactly the same. So the total torque, add those two together and the 1/2 plus 1/2 becomes 1. I like that about math. And I'm going to sine 90 degrees as 1, so I'm going to drop that out. That is the equation for the torque for an electric motor, because that's what this is an electric motor. Now if we come back, what shape is my loop? It's a rectangle. Rectangle-ish, yeah. And what's the equation for the area of a rectangle? Length times width. Now, this is not a technical proof, but for this case, AB was the area. And it turns out, hand wave, hand wave, hand wave, that it's always true. That the net torque is equal to I times B times A sine of theta in the y-hat direction. So even if it's a circular loop, you just need to find the area of that loop. Yes?
Sine of theta is the angle between the radius and the force.
That's right. Sine theta is the angle between the radius and the force, which in this picture was 90 degrees. But if the coil rotated by 90 degrees, it would have been 0. So if the coil rotates by 90 degrees, what's the net torque? Sine of 0 is 0. So if it rotates by 90 degrees, there's no torque. This position, it has maximum torque of IAB sine of, not that IAB, I capital A, B, sine of the angle, which was just IAB. But you rotate 90 degrees, it has no torque. What would happen if I rotated past 90 degrees? It would reverse the direction. So if you take this and you start it where it is, it will come up to this position, and then it has angular momentum, so it'll keep going, but it'll start slowing down because the torque is against it. So it'll keep going until it gets here, and it'll just keep going back and forth like that. Is that a useful electric motor? I'm going with no, that's not a useful electric motor. So we're going to have to do something to modify this to make it useful. Otherwise, it just goes until friction makes it stop in the position of 0 torque. Let's go to the next slide before I get 7 slides ahead with only 6 remaining. So here I wrote torque is IAB. What's missing from what I did on the previous page? The sine of theta. That's because this is the maximum. If I do more than one loop, each time I have the wire coming, I have the current I. So if I have 5 loops, I would have 5 times this torque. And so we just generalize it to say for n loops, my torque is n IAB, or I always write this way so I can remember it. I NBA, that's the maximum torque. And the torque for any angle, you would just add the sine theta.
What are the turns? The loops you put?
Turns is the number of loops you have. So if you have the wire just doing one loop like we had in our preceding picture, then n was 1. But if you had the wire so it comes out, goes around, comes around a second time, and then goes, then you had 2. So here's where the pictures start including the angle. You can see, hey, as it rotates, we're going to have the perpendicular distance is smaller than the total distance. And so that's where the sine comes in. We've already done that, so I can skip through these 2 here. And yeah, we've already seen this equation, right? Yay. So how do we get around the problem of the electric motor wanting to come back on itself? It's the electric motor. Yeah, right? Now that's an AC induction motor. These people over here did something that was also related to a motor. Theirs is more of the DC type. When you make an actual motor, you need to do something that's going to make it so the current changes direction. So I have that rotating piece. If the magnetic field is like this, when it gets to this direction, then the torque is, okay, I got to think about the directions we had before. Yeah. Yes. If the magnetic field is like this, when it gets to this direction, the torque is 0. But if it was rotating, it's going to keep rotating a little. So if we change the direction of the current at this position, then when it gets past that 0 torque position, the torque will make it keep going instead of make it stop. So we need something to reverse the current direction. What's the simplest way of doing this? The simplest way is to just use an alternating current, a current that goes back and forth. And if you use an alternating current, the frequency of your current will be the frequency of the motor, as long as you have enough torque to make it keep going. So one way is making an AC motor where your frequency matches the frequency you want to rotate. But the other is what we call a split armature. You have wires that come out like this to make the loop. Pretend that's a symmetric loop. If we just zoom in and look at the end of this piece, what we have is generally a circular rod, and then on that circular rod we actually affix, come on colors, we affix one, one wire here and a second wire here. And this whole thing is rotating. So the red wire is on right now your left side, the green wire is on your right side. And then we just put a brush. And we'll take a brush here. I'm going to make my brushes black. And I put a brush here that's connected to positive and a brush here that's connected to negative. So right now, the red side is positive and the green side is negative. But when it rotates and does half a turn, what's going to happen? The brushes stay put, but what happens to the red and green? They switch sides. So what happens to the direction the current is going? It flips as well. And so we're always going to have our torque the same direction by having this thing that's called the split armature. Why is it split? Well, because there's no electrical connection through there. And so we have the wires that make contact, and then they'll break instantaneously and make contact with the other side. You need to break both wires at the same time so you don't end up having a short situation for some brief period of time. So that split armature will allow us to have a DC motor, a motor that we can just connect a battery to, and by our construction, it will sit there and spin. Now these motors are, of course, ubiquitous to everything we do. I mean, I have in my pocket a cell phone. Does it have an electric motor in it? Yes. What does it have an electric motor for? Yeah. It's going to vibrate if somebody gives me a call. And it has in there a little electric motor to make it go bumpy, bumpy, bumpy. And you can actually, people do, control the motors in here to make the phones, they can make the phones walk and things like that by controlling the motors that are used for that vibration. I say motors, I think there's more than one. So the electric motor is in just about everything. In the projector, there's a fan, and that fan has an electric motor. The fan is just blowing air so we can get some convective cooling off of that bulb because it's producing a lot of heat. So electric motors are everywhere in our world, and you can see it's a pretty simple concept. Now, it doesn't have to stay simple. If you look at those two posters, you'll see that they're not super simple. One of them has some flaws in its theory. I'll point it out because I don't want to embarrass people. So don't take them as gospel correct. But, you know, motors can be very complicated. If they were simple, there wouldn't have been the flaws in the theory. All right, we're done with the week of school. I will have a homework assignment due on Monday when you get back. I know that probably no one had started the homework assignment or had looked to see the homework assignment that should have been due today until, probably now for most of you. But it's still not fair for people who are trying to stay up to date with things if you wait until, less than 24 hours before it's due and say, oh, and here's an assignment, right? I want you to have time to do them. So that's why there's no assignment for tonight.